All right, let's talk about a machine that you've probably never seen up close, but I guarantee you've touched something it made today. We're diving into the lathe, truly the unsung hero of our modern world. I mean, it's been called the mother of all machine tools for a reason. Think about it. The engine parts in your car, the components in a satellite orbiting way above our heads, all those incredibly precise, perfectly round parts that make everything tick. Yep, they almost all started their life on a lathe. So, what does this thing actually do? And maybe more importantly, why is this ancient sounding machine, a centuries old concept, more essential now than ever before? Well, that's what we're here to break down. Okay, first up, this is a world-shaping machine. And I mean that literally. To really get a handle on the lathe, you have to appreciate just how massive its scale is. Its impact is, well, it's everywhere. The best way to picture it is like a potter's wheel, but for metal. Seriously. At its core, you have a chunk of material, usually metal, but it can be other things too, spinning incredibly fast. Then you bring in a super sharp, super hard cutting tool, and it just shaves away the material with incredible precision. It's all about creating something perfectly round. And that one simple idea, spinning and cutting, is the bedrock for so many essential industries. We're talking automotive, aerospace, medical, you name it. Engine pistons, aircraft landing gear, turbine shafts for power plants, even the titanium implants used in surgery. The list just goes on and on. A good rule of thumb, if it's a precision part and it's round, there's a really, really good chance a lathe was involved. Okay, so how do we get from a rough block of metal to a super precise part? Well, it's not just one single action. It all comes down to a handful of fundamental operations. And the main event, the number one operation, is called turning. This is the lathe's signature move, right? The cutting tool moves right along the length of that spinning workpiece, just shaving off material to reduce the diameter. This is how you make things like shafts, axles, pins, basically any long cylindrical part you can think of. But here's the thing. A lathe is no one-trick pony, especially modern ones. They have this thing called a tool turret. You can think of it like a robotic octopus arm holding a bunch of different cutting tools. It can swap them out in a split second to perform all sorts of different jobs on the same piece of metal. It's what allows for really complex parts to be made all in one go. And this versatility is really its superpower. So beyond just simple turning, you can do things like facing. That's when you create a perfectly flat surface on the end of the part. Super important for anything that needs a tight seal. Then there's grooving, which is just cutting a narrow channel, for things like O-rings. You've definitely seen knurling before. It's that crisscross, grippy pattern on tool handles. And maybe most importantly, thread cutting. Yeah, this is how we make the threads on pretty much every screw and bolt in existence. Now, the basic idea of a lathe has been around for ages, but the way we control them, that has gone through a massive revolution. This is really about the evolution from pure human skill to the precision of computer code. So you've got two different worlds here. On one hand, the conventional or manual lathe. This is all about the machinist. It's an extension of their hands, their eyes, their feel for the material. The precision comes directly from their years of skill. Then you have the CNC lathe. That stands for Computer Numerical Control. This machine doesn't rely on feel. It relies on a computer program, G-code, to tell it exactly what to do. It can repeat a process thousands of times with mind-boggling, micron-level accuracy. This is the workhorse of modern manufacturing. And you can really see the difference. It's moving from this very physical, hands-on world of turning wheels and pulling levers to staring at a screen of code. The job of a machinist has totally transformed. It's less about being a hands-on craftsman and more about being a programmer, a problem solver, and a process manager. But you know what? Whether it's a skilled machinist turning the wheels or a computer running code, the final quality of that part still boils down to mastering a few key variables. This is where the real art and science of the cut happens. Right, getting that perfect mirror-like finish isn't just about forcing a tool into metal. It's like a delicate dance, a balance between the tool, how fast the part is spinning, and how fast you push the tool forward. And if you get that balance wrong, you're not just going to get an ugly part. You could literally break your cutting tool or even damage the entire machine. So let's break down the two main players here. First, you have cutting speed. That's simply how fast the surface of the workpiece is moving past the tool. Then you have feed rate. That's how quickly the tool itself is advancing along or into the part.
Get them wrong and bad things happen. If your cutting speed is too high, you generate a ton of heat, enough to destroy the tool. If your feed rate is too aggressive, you'll get a terrible surface finish. It is a constant, delicate balancing act.
And this balancing act is totally different for every single material. Just look at this chart. For something soft like aluminum or plastic, you can run things super fast. But try that with a really tough material like titanium? No way. You have to slow everything way, way down to handle the incredible heat and force. Every single material has its own secret recipe, its own sweet spot for getting that perfect cut. Okay, we've talked a lot about the cool stuff, the precision, the power, the tech. But none of that means anything if you're not safe and if you're not taking care of the machine. This is the foundation that makes all that precision possible. And let's be crystal clear about this. Rule number 1, always, is safety glasses. No excuses. You've got a heavy piece of metal spinning at hundreds or even thousands of RPMs, and you're literally slicing bits of it off. Tiny, razor-sharp, and often red-hot chips are flying everywhere. Eye protection is non-negotiable, period. Now, this next one might sound weird, but it is one of the most critical safety rules around a lathe. No gloves. I know, it feels wrong, but here's why. A spinning machine part can snag a loose bit of a glove in a fraction of a second, and it will pull your entire hand in before you even know what's happening. Entanglement is a huge, huge danger here. So personal safety is job 1, but the health of the machine itself is what guarantees good work. You want precision? You need a disciplined maintenance routine. You got to check the lubrication. Without it, things grind to a halt. You've got to inspect parts for wear and tear, and you absolutely have to clean up all those chips and debris after you're done. It's a consistent routine that keeps the machine accurate and reliable. And this quote from Zappium really hits the nail on the head. A structured checklist turns an often overlooked routine into a reliable process. Once that rhythm is set, reliability follows. It's all about building that rhythm, that discipline, because in this line of work, reliability isn't just a nice to have, it's everything. So there you have it. A machine that started as a simple concept, spinning something and cutting it, has evolved into this incredible high-tech powerhouse of manufacturing. It's this amazing mix of raw power, human skill, and now digital programming. It really makes you wonder, as our technology and materials get even more advanced, what's next? What will the machine that literally shapes our world create for us tomorrow?